we're going to start with a little bit of background. Dam and levee structures have been talked about a lot lately. Of course, we've got a lot of dams, a lot of levees, both in North America and around the world, and they're pretty critical to our infrastructure. They're providing water supply, they're providing flood protection, they provide a host of valuable services to the general populace. There are a lot of costs associated with the dams and levees and canals, pipelines, all these things that we have to hold and convey water. The costs have been racking up in the years, and shortcuts have been taken on maintenance, and as a result we have a pretty good awareness of the risk of failure around the nation and around the world. In North America, there have been a lot of recent headlines from the ASCE Infrastructure Report Card, several professional organizations, state dam safety officials and dam safety organization, as well as from various levels of government, outlining both the positive results of having dams and levees, but also noting the risks and the level of expenditure required to keep populations safe and to keep our dams and levees functioning properly. Pretty much everyone acknowledges the need for serious investment in dams and levees and the need for engineers, especially flood and emergency action planning related engineers, to estimate our risks of flooding and of catastrophic failure. Given the grades that are out there, which you see on the screen here, water and environment dams, we've got a D in North America on the level of maintenance and of safety that has been put into the dams. 2009 we've got a D- on levees and a D on dams, and the investment needs to keep our dams and levees safe are significant, especially in an economy where there's not a lot of extra money to go around. It is projected that there will be a significant shortfall in upgrading and in maintaining the dams and levees that are around us. So with that bit of background, I think that most everyone that's logged on today recognizes the need to prioritize the maintenance and the upgrades of our dams and levees. And one way to prioritize that maintenance is risk assessment, and modeling forms a critical part of that. Modeling dam and levee failure can help us understand the risks and the costs associated with each structure. Based on the highest risk, then we might target the funds to maintain or upgrade those dams and levees that would have the greatest impact if they were to fail. In the past, modeling has been done on dams and levees, and it's been good given the technology that we had. But there have been a fair number of limitations in the past, and because of those limitations, we may not understand really well the risk involved in the breaching, the failing of dams and levees, and we may not understand the cost of the flooding that would result. 1D models have been used primarily in the past, the dam break model, the flood wave model from the National Weather Service, of course HEC-RAS itself. These tools have provided some tools for catastrophic failure modeling. A lot of them have been used in steady state mode, which I'll talk about some of the limitations of that. And one of the primary problems that the 1D models have had in the past would be, given the uncertainty of where water will go, it's pretty difficult to put together a 1D model that's representative of the center line of flooding, for example. Another limitation we've had in the past is there hasn't been a lot of robust research on physical breach development. So how does a breach actually form? How fast? What are the characteristics of the failure itself? Now, of course, if we don't quite understand the physical breach characteristics, then we've got to make some assumptions and we've got to estimate the kind of water that will be released from a reservoir, from a river, from a canal. Another item, I guess really a list of things that past simulations and past technology has ignored. Steady state modeling has ignored timing of flood wave propagation. It also ignores the volume of water available for spreading, and thus gives us pretty close to absolute worst case scenarios. And while that's nice, that's certainly a conservative approach, there are difficulties in that we've got to prioritize our spending. We can't fix everything everywhere, and so having a worst case scenario when we do our modeling doesn't give us a true picture of what's going on. In the past, we've also had some limitations in mapping. When we've used 1D models, it's been difficult to extrapolate 1D results to make a map that's meaningful on a three-dimensional land surface. So anyone who's done a HEC-RAS model would know that getting the 1D model results and converting that into a flood map that tells you where's the flooding going to be and how deep is it going to be is a fair bit of work with a GIS system or a CAD system or a hydraulic model system that might help create that map. Nonetheless, there's work. There's work involved and there's extrapolation involved. So with those comments on what's has happened in the past, there have been improvements in recent years. One of the most significant improvements to dam and levee breach modeling has been the use of full dynamic analysis. So rather than using steady state models, more and more people have recognized the need to use dynamic models that account for timing and volume of water in the rivers and in the reservoirs. Most of these models would be based on the St. Venant equations and can be done, the St. Venant equations can be applied to both one-dimensional and two-dimensional models. And that's a real benefit. The unsteady HEC-RAS or the National Weather Service, their flood wave program, you run those in dynamic mode, and you're going to get a lot better picture of flood wave propagation and volume, a little more accurate than your steady state models. Going a step further, full dynamic analysis including hydrology is even better. We can input the rainfall events that may be triggering dam breach and levee breach, and we can do the rainfall runoff calculations linked with the hydraulic calculations in the river or in the canal, and putting these things together, we come up with an integrated model that can represent rivers, pipes, streets, overland flow areas, just general land surfaces. By integrating these things together and applying an appropriate analysis engine, we can get a more accurate picture of what's going on in our rivers, and then when there's a breach or a failure, then we can see where that water goes across the floodplains and across maybe just open land. So this has been a goal at XP Software for many years. We started with full dynamic analysis way back at the very beginning with XP Swim and XP Storm. That was one-dimensional, fully dynamic analysis. And then in about 1996, I believe it was, we released a 2D module which also allowed fully dynamic analysis. By linking the 1D and the 2D within XP Swim and XP Storm, we now have a truly integrated modeling system where analysis of hydrology and hydraulics is possible throughout the entire system, and events like breaches and failures and surcharging of drainage systems is a lot easier to track because it's all done in the same software, it's all done on the same set of data, thus making a very robust system. All right, well, I'm going to step through several examples today looking at XP Swim and XP Storm tools for integrated one-dimensional and two-dimensional modeling. As I said, this modeling would be based on a fully dynamic analysis, meaning it's not steady state. I won't talk much about hydrologic simulation today, although those options are in there. I will note the hydraulic options, the hydraulic simulation options that are available to represent dams and levees and pipelines and the breaching mechanisms that may occur. So I'm going to launch into that, and let's have a look at some things. The first thing I want to talk about is in relation to dam and levee breach mechanisms. Now, there are many modes of failure that may occur on a levee or with a dam. Overtopping, you might get piping. As the picture shows, you can get seepage underneath that then causes sand boils and eventual erosion. The way that a dam or a levee breaches, sadly, is not fully modeled in XP products. So the physical breaching is still an area of research for several organizations, and ourselves included. Where we're trying to get with breaching is ultimately arriving at a flow versus time, or a hydrograph, and a total volume that we expect through the breach. That can be done independently, outside of XP products. There are a lot of rules of thumb. There are a lot of people that have their own little analysis that they prefer to calculate the water that would be released in a breach event. There are also some simple options in XP software that I will show you to physically model a breach, but there are many improvements needed and many improvements coming, I think, in the industry to better analyze the physical breaching. Let's jump in and let's first talk about dams. I'm going to talk about dams and levees separately here, although everyone, I think, will recognize that there are a number of commonalities. I think that a couple things I've already said. Dam breach assumptions are often made externally, but once we make some simple assumptions or decide how we're going to go with our breaching, the flow from a breach in XP products can be handled in several ways. We might send flow down a channel, a one-dimensional channel. We could send flow from a breach to the 1D channel, plus letting it spill to overbanks. We might also send the flow from a breach directly to a two-dimensional domain and letting it spread and go where it will. So flood wave propagation can be modeled in, as I said, dynamic flood wave propagation. It can be modeled in 1D or 2D or a coupled 1D, 2D. This is, the point of this then is to aid flood mapping and emergency action planning by being able to see how deep, how fast, and where did the water go as a result of the breach. Let's look at the first option. A river, a 1D river with a breach hydrograph. So what does this mean? On the screen, you would see the representation of a pretty simple model. Up in the upper left, or excuse me, the upper right corner of this model, you can kind of see the embankment. This is a debris basin. It's a fairly large debris basin at the mouth of a canyon, American Fork Canyon in Utah, near where I used to live. I lived up on the bluff overlooking this river channel. The river channel then in this scenario would be modeled much like a HEC-RAS model. We've got a center line, we've got cross sections. What we're lacking is what is the flow that is going to go down that channel. One way to do that is simply to input at the upper end, or the upstream node of our model, the breach hydrograph. Where do we get the breach hydrograph? Well, in this case, what I assumed was a fully open outlet structure on this debris basin, followed by the gate itself being torn off, so being removed entirely, thus opening the spillway completely, which of course is not designed to happen. That hydrograph is fairly simple calculation given that we've got the data on the debris basin itself and the outlet structures. We can then plug the hydrograph. You may not be able to see that hydrograph really well in that picture, but the hydrograph varies from 0 up to about 1,700 cubic feet per second, and then back down. Now, if we do this, the model is then going to allow, or going to compute the timing and volume as the river overflows or spills out into the downstream channel. What we won't get here is lost flow calculation. So if it occurs that the hydrograph I try to send through this river channel actually exceeds the capacity of the river channel as set up in 1D, I'm going to have some lost flow, and that's not going to work out. However, I wanted to show you this one simple option for breach modeling. Simply input the breach hydrograph at an upstream node, or really any node in the model, and let it run, and it will model that hydrograph down through the system. A slight variation on this would be taking a 1D river and using a storage function in a 1D model in conjunction with a real-time control, RTC. So in this same model, up at that debris basin in the upper right corner, I could designate the storage of that debris basin, a simple storage capacity curve, which is available in this case for that debris basin, and then in the XP swim interface, or the XP storm interface, I can apply a variable weir or orifice or rating curve at that upstream node. What I mean by a variable weir, orifice, or rating curve is that I can have that change over time. So the weir could start out at a certain level and over time erode down to to an invert level of the basin, essentially washing away part of the embankment. Similarly, an orifice could be used to model a piping failure where we gradually open a flow area and it gets bigger and bigger over time. Once again, we're going to have timing and volume accounted for as the flow is released to the river channel. We still could have lost flows, so that's not good news. But the way this is done in XP Swim is fairly easy. At an upstream node, I can simply check on that I've got a weir, and I've got an orifice, and the storage at that node then could escape through this weir or orifice. Now the weir and orifice I could then designate in my real-time control dialog. I'm showing one of the examples here where this is the spillway or the weir. I'm saying the control, a weir, and the name is spillway. That's what I named my weir when I created it. I'm going to dynamically change the weir crest elevation. The weir crest elevation starts changing at 30 minutes into the simulation and ends at 45 minutes later. So I've got a 15-minute failure time here where the weir is going to go from 22 feet in elevation down to 18 feet in elevation. So we're going to erode away 14 feet of that weir in 15 minutes, essentially knocking down the spillway to the invert of the debris basin. When I do this in 1D, what I get would be 1D modeling results. So I'm showing here on the screen a simple slide showing the long section view of the river. And of course, with 1D results, you can see the flood wave move down the river. Let me start that again. The flood wave moves down the river. You can also see in the lower left the cross sections in the river and where the where the depth is in each cross section as the flood wave propagates down there. Finally, in the lower right, those are actually graphs of depth versus time at each cross section. So there's a variety of outputs that XP Swim or Storm can provide for 1D results. Of course, you might have noticed, maybe some of those of you with a sharp eye would notice when that animation happens, a few of the cross sections that we showed actually hit the top end, and that means that I've lost some flow. When water level reaches the top edge of your cross-section, chances are you're imposing some false assumptions. You're starting to impose a vertical wall, an imaginary vertical wall, on the top of your cross-section, and that's not accurate. So maybe we go to the next stage of breach modeling with 1D. What we'd like to see, rather than a 1D profile view or cross-section view, is something like I'm showing on the screen now, which is the result of water being released from the detention basin. You can see that detention basin in a little more detail here in the upper right corner. I'd like to see that water escaping and being allowed to both follow the channel, which you see in the yellow and the green colors, as well as being able to escape and go out into the floodplain that might not be reached by my cross-section. How do I get my 1D modeling results to do that? Well, I can make big cross-sections and then take my 1D results and go to a GIS and start extrapolating and then creating a flood map. Or I might use the next option in XP Swim or Storm, which would be, let's link our 1D river and the breach in our 1D river to a downstream channel that is allowed to overflow to the overbank areas, which are represented in a two-dimensional manner. What I'm showing on the screen now is the upper end of a highly urbanized channel. You can see in the upper right corner there is a reservoir in the corner of the city. If we were to breach this reservoir and allow it to travel down the 1D channel, you can see in the 1D channel there are a whole lot of cross-sections. On this curve you can see some of them spaced out, but there's a lot of cross-sections down through that channel. But what will happen if we breach that reservoir is that that channel will not hold the breach hydrograph. Along the edges of the channel you might be able to see a blue line. That blue line is what we call our interface line between a 1D channel and the two-dimensional overland. So what it allows XP Storm or XP Swim to do is let the water out of the channel and let it run across the land. The next slide here will show the effects of linking your 1D river with 2D and allowing overflows and spills to exit the channel. Now keep in mind that I've still used the same breaching mechanism as I would as I showed previously. I simply input a breach hydrograph that was calculated outside of XP Swim or Storm, or I used a variable weir or orifice to simulate failing, a physical failing, and releasing a pool of water. Either way. Now, what happens, you'll see as I run this animation, is that water comes out and stays in the channel for a bit, gets deeper, and then starts to escape the channel and propagate through the overbank areas. In this case, being a highly urban area, you can see that the water starts to travel down the streets and around buildings and so on. So here's an example taking a one-dimensional river breach, river-type breach where we breached the dam, let it go down the river until the river channel couldn't hold it. It escaped out to the sides and propagated. So that's a fairly robust and popular way to do the dam breach modeling. I did want to show you an option where maybe you've got a breach from a one-dimensional channel or a pipe, one-dimensional pipe, and that water is released directly to a 2D model. In other words, there is no downstream channel to worry about. It's just a breach out into the floodplain or to the field surrounding a reservoir. This is great for rapid emergency action planning. So simply saying we're going to fail and see where the water goes, and we want to do that quickly and easily. It works really nicely, and it's easy to do. Once again, timing and volume of the spill is accounted for, and the undefined flow path is not a problem. The spill, the breach occurs at a location, and the water will find out where it needs to go by, we're analyzing the land surface and letting the water run. I'm going to show you a pipeline case and then a dam breach case. the first example here. On the upper left, you will see some arrows and nodes. That represents a pipeline. It's actually a very large aqueduct that supplies drinking water from a reservoir through to a drinking water treatment plant. And the pipeline is about 18 miles long. And in the locations, you might be able to see the red dots or this orange and yellow crosshatched area. That's where that pipeline actually is above ground. Mostly it's buried, but in areas where it has to cross some rather severe terrain, some gullies on a rather steep hillside, the pipe actually is up out of the ground. So what would occur if up that pipe, which is, if I remember right, it's a 60-inch pipe. What happens if that 60-inch pipe running at about 150 cubic feet per second, what if that is breached? For whatever reason, there's a heavy rainfall and a lot of debris comes down that gully, hits the pipe, and starts a breach. This is fairly easy to do. At the location, we simply can give the dimension of the pipe and the flow in the pipe, and actually let XP Swim model the entire pipeline, model the draining of the pipeline, assuming that someone could get off and shut off the headworks of the pipeline within a reasonable amount of time, which is, in this case, prescribed in the operations manual of this pipeline. Someone could go shut that off fairly quickly. However, it still would drain the entire pipeline down to this point. And XP Swim will compute that hydrograph that comes out of the end of this pipe if it were to breach. Here's the result. The breach is in the extreme upper left, and the water, you can see, actually comes down the hill, finds a low spot. In this case, it actually travels right by the fire station and City Hall of this little town. And where it's traveling right through the, in fact, it's pretty much clipping the corner of City Hall, and that's where the fire station is. The doors to the emergency response vehicles are right there. The water in front of those doors, in this case, reaches a depth of about 3 feet. So you wouldn't want to drive your vehicle out through that. And you can see the water continues down to the right side of the screen and is ultimately caught by a natural channel, a creek that is running through the country, through the fields. It's caught by a creek and then actually empties into a large canal down at the right end. But very quickly, we can load the terrain data into XP Swimmer Storm. We can put together the pipe with a few links and nodes, breach that, and run an analysis and show where the water will go, how deep and how fast, who's going to be flooded. And I personally put this model together, and it took me about 40 minutes to collect the data, input it, and then run the analysis, which took 6 or 7 minutes in this case, and created, this is the worst case, the maximum flood extent of that breach. I wanted to show the animation of this breach to you, but I found when I tested some animations over the webinar here, they were really, they're a bit jerky and choppy, so it didn't make a really pretty picture. So just showing you the final result there. So there's a case of a pipeline, a single point failure of a pipeline just being dropped right on the ground and traveling. Similarly, I could do this breach with a reservoir. This screenshot is of Black Canyon Dam. Black Canyon Dam is near Emmett, Idaho, where I grew up, and it's not a big dam. It's largely an irrigation dam, but it does hold back a fair amount of water. And frankly, it was built in the 20s. And it's received some upgrades, but there hasn't been a whole lot of attention or worry about it because it's not a big dam, so people feel pretty safe. In this model, what I'm showing is that at the location of the dam, I simply put a one-dimensional node, and I specified the storage of that reservoir. Here in the node data dialog is what I'm showing you. I've clicked on the storage button, and I put in the storage capacity curve of that reservoir. I got the storage capacity curve from where? Well, I got it from the Bureau of Reclamation, who operates the dam. So I'm saying, let's assume that the reservoir is essentially full, and then what I applied was a real-time control saying I'd like to lower the gates. This has radial gates. Let's open the gates to their maximum capacity, and then let's overtop the dam on top of that. So I did that with real-time controls, and the snapshot there on the right side of the dialogues would once again be the maximum flood extent if we were to have that situation at this dam. Now, that is it's actually a concrete dam. We could model catastrophic failure of that concrete dam also with a with a real-time weir, essentially doing a blasting open of that weir in a quick way right down. In that case, then of course the water just goes further and faster. You'll note I did not put a one-dimensional channel downstream of the dam in this case. I'm showing on that graphic the center line of where the river actually is, but as you can see, when this much water goes shooting down there, the channel itself is relatively small and is adequately represented in the two-dimensional model covering the entire valley. So there's a case where you can breach a dam using real-time control, using the one-dimensional options, and let that water go. Now, what about 2D dam breach modeling? In other words, I don't want to use any 1D. The 1D options aren't any good. What I'd like to do is simply define the land surface and even define the dam in the two-dimensional model. So the terrain of the dam. This would be, quite easy to do for a large earthen dam, where the embankments are actually very large and can be adequately represented in a two-dimensional model. If I've got that in the two-dimensional model, I can specify an XP swim one of two things. I can either specify a flow condition along a line. So, for example, along the crest of the dam, I can specify flow or head that's an overtopping condition. What is more common would be I can simulate a terrain breach. So the two-dimensional model allows me to designate an area, whether that's the entire dam, a certain portion of the dam, and actually tell it, go ahead and erode the land surface away. So in this case, erode the dam away over a period of time and empty the water, empty the pool of water behind that dam. This is done completely in two-dimensional modeling. So the flow is going to spread out on 2D, and the key here is you need a good 2D model with accurate terrain and, of course, an accurate dam representation. I'm going to show you here not a big earthen dam, but a small dam that actually exists that people didn't know existed. This is a fairly urban area, and I'm going to run this animation for just a second, see if I can stop it, show you what I'm talking about. So over here towards the upper right, you see this red spot. This is a case where an extreme rainfall event is occurring, and there is an embankment along the road here to protect these neighborhoods from having to look at the big industrial ugly buildings on the other side of the road. So a nice berm was built, an embankment built for aesthetic reasons. You find that in an extreme rainstorm, a fairly substantial pool of water will form behind that berm. Now, what was done in XP Storm is a 2D model was built, and right at the along this berm, there was the low point of that berm was selected, and essentially what was done was when the water level in the pool behind the berm reaches the top of the berm, there is an erosion event triggered. As the overtopping occurs, it's going to erode down that berm to the base elevation. And you'll see that here. I'll go ahead and run the elevation. You'll see it's a rather extreme event. So the water builds, the breach happens, and the water blasts down through around the buildings. And in this case, the whole point of this model originally was to protect some proposed apartment buildings down here right on the bay. So the apartment buildings, they were going to put a little flood wall around them to divert water from the street flooding and so on. And that works really well until we have a little breach event of this berm that overwhelms that flood wall and ultimately floods the proposed apartments. So there's a case, pure 2D model. Just put the surface in there and let XP Swim or XP Storm model the erosion of the berm. Now, I know a lot of people are going to say, well, how accurate is the modeling of the erosion? And look, it's pretty much user controlled. You're going to indicate when it's triggered, so the top level of the berm. You're going to tell it how far to erode and the time to open that breach. So once again, we don't have the capacity to do that geotechnical physical modeling in XP Swim or XP Storm. We've got the capacity to show the terrain effects and the hydraulic effects of that breach. Okay, so those are some dam options, breaching of dams. Let's talk now about levees. So levee breaches, slightly different topic. Levee breaches, typically we're talking about a river that is running, and the side of the river, the embankment, is overtopped or is breached for a variety of reasons. The levees then are typically protecting, of course, low-lying, flat areas that are certainly not characterized by obvious flow paths. Once the water's out of the levee, it spreads out, it goes everywhere, and in some cases, there are sump pumps behind levees trying to pump water back over the levee. There's a variety of things that are occurring behind levees. So how can we model the river in XP, Swim, or Storm, and then the breaching of a levee alongside the river? Let's look at that. First off, a fairly simple way would be creating a river model in 1D. What I'm showing on this screen is a one-dimensional river model. You can see along the curve of the river here, we've got a center line, we've got cross-sections along the river, and that river is protected by two large levees on either side of it. I shouldn't say the river is protected. I suppose the neighborhoods around the river are protected by those large levees. I can simply designate a node location along the river where I want to let water out. So using the one-dimensional options, in this case I chose this where this red arrow is. I'm saying right here at this specific location, which is it's a low point on the levee, I am going to use a variable weir or an orifice or a rating curve and simply let water out. Rather than continuing on down the river, water could go out if it overtops the weir or orifice, if it meets the conditions that I've allowed. Once it's out of the river, then it's going to be handled across the land surface with a 2D model. And in this case, you're seeing there's actually a one-dimensional model of a drainage system, an interior drainage system behind this levee. So we could get flooding behind a levee because this system backed up, but if this levee overtops or breaches, that's going to be a much more significant flood event. And it's pretty simply done by setting up the river and breaching. These are the same things I talked about a minute ago with one-dimensional to one-dimensional breaching. Just put in the controls that says, the weir or the levee erodes away from this level to this level, and let it fly. The water is going to spread out. Second option I wanted to show is, what about a river with a two-dimensional levee overtop event? So I can put together a one-dimensional model of a river But what I want to do is in the 2D overbank areas, I want to actually model the overtopping of the levee and the erosion of terrain that lets water out of the 1D river. So here's an example. This is zoomed in fairly close, where you can see it's a fairly small river channel, more of a stream that travels from south to north here. Over to the right-hand side of this channel, there is a school with playing fields and so on that have been exposed to significant flooding in the past. What was proposed is that a flood wall was built around the school and the playing fields that would protect it from flooding. What I'm proposing to model here is what happens if a section of that wall breaches. So the wall is put up in sections between posts. Let's assume that we overtop a section, where the land dips down. We overtop a section and actually let that fail. What would happen? The way this is set up in XP Swim is we can designate, this little brown box designates the area that is going to fail, and this little target with the link, what we're saying is we're going to tie this failure to the depth of water in the river, in the 1D model. I believe, let me see, I think I have this in XP Swim itself. You can have a look at what happens. So here's XP Swim with that same model. I'm going to zoom out one, and you can see now the more full extent. There's a protective wall all the way around that area, and we're just a little bit in. I'm going to see if I can run this animation and see how it comes across to you. The water in the channel here is going to get deeper and deeper, and what will happen is as it starts backing up against the wall, the flood wall, at some point it gets deep enough to where it will overtop, and when it overtops, you'll see the water release into the playing field area. So still spreading out. You can see it spreading out into the neighborhoods, up the streets. The playing fields are still protected. There's the breach, and the water then quickly spreads out over that area inside the protected area. So there's a nice example of how you can take a one-dimensional river model and then pick an area out in your two-dimensional, your two-dimensional model area, whether there's a flood wall there or there's a berm, whatever it is, you can essentially tie the water level in the river to a failure point, and when XP Swim calculates the river has reached that trigger level, the failure will occur. Once again, that failure, how does it occur? You're going to have to input things. In this case, let me just show you what was put in there. I'm going to turn off the maps. And if I select that shape, I have to zoom in a bit here. So I select that shape. What I've designated here is that when the water level at the trigger point, so I designate where the trigger point sits, when the water level at the trigger point hits 42.5 meters in this case, so the water level is 42.5 above sea level, at that point we are going to lower current elevations. In other words, we're going to knock down that wall to 41.5, which is this ground surface elevation there. Going to knock it down, and it's going to take about 15 minutes to erode that, to knock it over. So it doesn't happen instantaneously. It could happen instantaneously if you want to. Time to reach final elevation, if you put 0 there, you've got an instantaneous breach, a catastrophic failure of a fence or of a wall. It'll fall over and water goes right through. So there's an example, letting a river, letting a channel breach through a certain point. Let's jump back to slideshow. I want to show you the next option. What about using a fully two-dimensional model? So the river is modeled in 2 dimensions. The levee is in a 2D model. And what we want to do is simply knock down a big chunk of levee and see where the water goes. So again, what I'm showing you down below the text there would be the large brown area is the area where I'm saying this is the section of the levee that's vulnerable. How do you know it's vulnerable? Well, there's been a lot of people out for months and months punching holes in levees all over the country, trying to ascertain where those danger points are. That's analysis that would have to be done outside XP Swim, or in this case, this is simply the low point of the levee where it dips a little bit, where it would be. This is where it would overtop first, and if it overtops there and we erode away the levee in that area, what will happen? This again is fairly easy to set up. Let me jump to XP Swim. I'll show you in this model. I'll turn on the two-dimensional model. So in this case, the entire area is represented in a 2D grid. In the river, the overland, we're just going to model the whole thing in 2 dimensions. Well, of course, we have to have good terrain data for both the bathymetry, the bottom of the river, as well as the land surface. But the whole thing is in 2 dimensions. I'll turn that grid off so we can see a bit better. And then, as in the other case, the second case you saw a minute ago, this area that represents the top of the levee, I've designated that when the water level hits 23.7 feet, so that would be actually the top of the levee. When that water level in the river hits that point, we're going to start lowering the levee, so start eroding the levee down to a constant elevation of 22.5, which is essentially the land surface level at the bottom of the low point, or the bottom of the levee there, the vulnerable point. And in this case, it's going to take about 30 minutes for that breach to open. Now, in this case, and in the previous case, I just showed one area. I drew a box and I said, in that area, we're going to knock down an obstacle. You can do several of these. So one example here would be, what if you have multiple risk points along that river and you're not sure which one's going to breach? Well, go ahead and put in the possible breach points with their triggers. So when the water hits this level, we think we might have a breach here. The hydraulic model then will model the river, figure out the water levels in that river as they rise, and then it will, when it hits the breach points, wherever it hits the breach points, it's going to go ahead and trigger that erosion event, that breach opening event, and let the water go. So you don't have to just pick the one place. You can pick several points along a levee that are possible failure points, and insert the possible mechanisms of failure, whether it's erosion, whether it's, as I said, kind of one of those variable orifice type options where you're going to open up a piping failure, and let the hydraulic model do its job until it triggers one of those breaches, and then when the breach forms, it lets the water go out into the overland. Okay, so there we have it, levees. You can breach those levees from purely 1D perspective. Just let the 1D river, let a node in the 1D river just put some water out, and you control that. You can designate a one-dimensional level in the river, can then trigger an overtopping. You can also let a two-dimensional river model trigger an overtopping of a levee along a river. The one thing I haven't put together in this show is what happens behind the levee if it doesn't breach, but you start backing up your interior drainage system. So for whatever reason, the pump fails, it can't pump water over the levee. Can you get a flood inside a protected area that's not due to breaching? Well, of course you can. That wasn't exactly the topic of this webinar, so I didn't go in there, but it should be noted that that when you've got a levee and you've got a river, you're doing a 2D model, a 1D 2D model in XP Swim, you can also model that interior drainage and the flooding that might occur behind the levee simply because you can't get water into the river because the river is so high. All right, regardless of what mechanism you're using here, whether you're doing dam breach, you're doing levee breach, you're doing a pipeline breach, and using any one of the options that I've showed you today, XP Swim and XP Storm with the 2D options are going to provide some great output. Inundation mapping, you've got controls on how you want to see that. Do you want to see depths? Do you want to see water surface elevation? What are the categories you want to see? Do you want to see where it's a foot deep and then 2 feet deep and then 3 feet deep? Do you want to see where velocities are highest? Another option, display option in the software. Show me the velocity vectors. In this screen I'm showing right now, I'm showing both depth and velocity. So, for example, you could see on the street, on the road here that goes along the waterfront, along the beach, there's a significant amount of water that is crossing the road at fairly high velocity here. So we would know we don't want to drive our truck through that area. Our emergency responders cannot get through that intersection because the velocities and depth, that combination is simply too much. That kind of output is fairly simple once you've used one of these breaching options in XP Swim and XP Storm with the 2D module. I know that there's probably a lot more detail we could go into today. I tried to cram all this into 1 hour, and it looks like I'm just a few minutes early. I got 55 past the hour. So that's the end of the brief overview. I should note that we are rolling out a more full explanation of these options in a one-day workshop that we're starting to offer at different locations around the country. The first one that we're doing will be in Kansas City in a couple of weeks, and it's being hosted by HDR, a consultant there who has expressed a lot of interest and put together a group of people, government officials, clients, other consultants, to come together, and we're going to go in and spend a day showing these options in more detail on how things are done. If you're interested in something like that, if you're a local agency or a consultant who wants to organize a continuing education option where we could come out and spend a day with a large group, typically 25 or more people is what we're looking for. We'll come out and go through the options in more detail. The levee and dam breach, obviously there's a lot of questions on that right now around the U.S. where there's a lot of flooding going on, but really around the world we're seeing a real push for this levee and dam breach modeling. So that's a quick view at what you can do with XP Swim and XP Storm 2D. And the breaching mechanisms, as I said, there's ongoing research. Those things will improve. But even as they stand right now, you can see there's a fair amount of power that is available to fully model a breaching event in 1D, in 2D, with pipes, with rivers, with overland flow, all of that all in one system. Thanks for coming today, wherever you are. Thanks for listening. Please let us know if you've got additional questions by phone, by email. Thank you all very much.